Welcome to Sleepy Origins. Tonight, we're exploring one of Earth's greatest mysteries. Where did water really come from? And why is our planet the only known world with vast liquid oceans? From ancient cosmic collisions to hidden oceans beneath distant moons, this journey will uncover the incredible story of water from the earliest days of Earth. Before we begin, leave a comment letting me know where you're watching from tonight. And, in your opinion, which place on Earth is facing the most severe water shortage today? More than 4.5 billion years ago, long before oceans reflected moonlight or storms rolled across continents, the young Earth looked nothing like the world you know now. There were no rivers, no clouds, no rain, no blue horizon separating sea from sky. If you could somehow stand on the surface of that ancient planet for even a few seconds, you would not see a world waiting for life. You would see something closer to a planetary furnace. The ground itself glowed. Entire regions of Earth were covered in molten rock so hot that the surface behaved less like solid land and more like a restless ocean of fire. Vast currents of magma moved slowly beneath a suffocating atmosphere filled with toxic gases. Volcanoes erupted constantly, not as isolated mountains, but as gigantic wounds stretching across the crust. The sky was dark orange and black, thick with ash, steam, carbon dioxide, sulfur compounds, and debris left over from the violent formation of the solar system itself. And above all of it, space was still crowded with destruction. Enormous asteroids and protoplanets crossed unstable orbits around the young sun. Some were small enough to burn into the atmosphere. Others were large enough to partially melt entire regions of Earth on impact. During this period, sometimes called the Hadean Eon, collisions happened so often that the planet may have spent millions of years struggling to cool down before another impact reheated everything again. Which creates one of the strangest facts about Earth's history. The planet we now associate with water may once have been almost completely incapable of keeping liquid water alive. At first, that sounds impossible. After all, Earth is defined by oceans. Water covers most of its surface. Human bodies are mostly water. Every known form of life depends on it. Even when astronauts search for alien life, one of the first questions they ask is simple: is there water there? But early Earth was different. Any water reaching the surface likely evaporated almost immediately. Temperatures may have exceeded the boiling point of water for extended periods, especially during massive impacts. Instead of calm oceans, there may have been an atmosphere loaded with superheated steam wrapping around the planet like a dense cloak. Some researchers believe the pressure and heat were so extreme that water existed in bizarre states unlike anything commonly seen on Earth today, neither normal liquid nor ordinary gas. And yet somehow, from this chaos, Earth transformed into a planet filled with stable oceans. That transformation may be one of the most important events in the history of the universe, because without it, nothing familiar to us would exist. No forests, no animals, no civilizations, no human memory. just rock, heat, and silence. What makes this story even stranger is that scientists still debate exactly where Earth's water came from in the first place. For decades, one of the leading ideas suggested that much of our water arrived from space. Not from rain clouds, but from ancient icy objects colliding with Earth billions of years ago. In other words, the water inside your body right now may once have drifted through deep space long before Earth even existed. Some of those ancient objects were likely comets, frozen remnants from the outer solar system, carrying water ice formed in extremely cold regions far from the sun. Others may have been carbon-rich asteroids, containing water locked inside minerals. During the violent bombardment of the early solar system, countless impacts struck the growing Earth. Each collision may have delivered small amounts of water over enormous spans of time. But the deeper scientists looked into the chemistry of Earth's oceans, the more complicated the mystery became. Certain isotopic signatures in Earth's water do not perfectly match many known comets. Some asteroid materials appear closer. Other evidence suggests part of Earth's water may have already existed inside the material that formed the planet itself. Minerals buried deep within Earth's mantle today still contain trapped water. In recent years, some discoveries have hinted that enormous quantities of water may remain hidden far beneath the crust even now, which raises an unsettling possibility. Maybe Earth did not simply receive water from outside. Maybe the planet had been carrying pieces of its future oceans deep inside itself from the beginning. That idea changes the way you imagine the early Earth. Instead of a dry planet waiting for delivery, it becomes something more complicated. A world slowly releasing hidden water from its own interior through endless volcanic activity. As magma rose toward the surface, steam and gases escaped into the atmosphere. Over immense periods of time, enough vapor may have accumulated for the planet to begin changing permanently. But even then, another problem remained. The young sun was weaker than it is today, yet Earth was still unimaginably violent. Massive impacts could potentially strip away portions of the atmosphere. Solar radiation bombarded the planet constantly. Without a stable magnetic field, some atmospheric gases could escape into space. Venus may once have experienced water as well, but today it is almost entirely gone, leaving behind a scorching greenhouse world hot enough to melt lead. Earth somehow avoided that fate, and scientists are still trying to understand exactly why. Part of the answer may lie in timing. Around 4.4 billion years ago, evidence suggests parts of Earth's crust finally began cooling enough for liquid water to remain stable at the surface, at least temporarily. Tiny zircon crystals discovered in Western Australia contain chemical clues hinting that liquid water may have existed shockingly early in Earth's history. These microscopic minerals are older than almost any intact rock formation on the planet. They survived from a world that otherwise vanished long ago. Imagine what Earth may have looked like during that transition. The surface still scarred by lava fields, volcanoes towering over unstable land masses, the atmosphere thick, dim, and hostile. But now, for the first time, rain begins falling onto cooling stone. Not gentle rain, not storms lasting days, potentially millions of years of rainfall. Steam condensed into clouds. Clouds released water. Water gathered in low regions. More water evaporated back into the atmosphere before falling again. The planet entered a cycle that would eventually shape every coastline and ecosystem in Earth's future. And this may have happened while asteroids were still striking the planet regularly. Some scientists imagine periods where oceans briefly formed, only to be partially vaporized again by catastrophic impacts. Earth's early history may not have been a smooth transition from fire to water. It may have been unstable and chaotic, oceans appearing, disappearing, and reforming repeatedly across unimaginable stretches of time. That uncertainty matters because it changes how we think about the origin of life itself. If Earth's surface remained hellish for longer than expected, life may have started later. If stable water appeared earlier, microbial life may have emerged surprisingly fast. There are even hypotheses suggesting life could have survived deep underground or near hydrothermal vents during violent planetary conditions that sterilized the surface. The deeper researchers investigate the beginning of Earth's oceans, the more the line between geology and biology begins to blur. Because water did not simply make Earth look different. Water changed what the planet was capable of becoming. It reshaped rock through erosion. It regulated temperature. It carried chemicals across vast distances. It may have helped complex molecules interact, combine, and eventually cross the invisible boundary between chemistry and life. And perhaps most strangely of all, water itself behaves in ways that still puzzle scientists. Most substances become denser when they freeze. Water expands. Ice floats instead of sinking. That single property may have protected Earth's oceans from freezing solid during ancient climate extremes. Water also absorbs enormous amounts of heat, stabilizing temperatures across the planet in ways that may have made long-term habitability possible. If its properties were only slightly different, Earth may never have remained biologically stable long enough for intelligent life to evolve, which creates a strange feeling when you step back and look at the bigger picture. The oceans can seem ordinary because they are everywhere around us. But when viewed against the scale of the cosmos, liquid water on the surface of a rocky planet may be incredibly fragile. Mars lost most of its water. Venus became a furnace. Many moons contain frozen oceans trapped beneath kilometers of ice. Across the solar system, water exists in forms that are inaccessible, unstable, or permanently frozen. Earth sits in a narrow balance between extremes, and for billions of years, that balance held. But perhaps the most unsettling part of this story is realizing how close the planet may have come to becoming something entirely different. A slightly altered orbit, a weaker magnetic field, larger impacts, different atmospheric chemistry. Any one of those changes might have erased the future oceans before they ever stabilized. You would never have known this world existed. No human history would have followed. No cities would rise beside rivers. No ships would cross oceans. No one would ever look up at the night sky and wonder where Earth's water came from. And somewhere inside that mystery is a deeper one still. Because scientists now suspect that water may not actually be rare in the universe at all. Enormous clouds of water vapor drift through interstellar space. Frozen water exists on distant moons and comets. Some exoplanets may contain oceans deeper than anything on Earth. In certain regions of space, water appears almost unavoidable. Yet planets with stable surface oceans may be another matter entirely. Perhaps the rare thing is not water itself. Perhaps the rare thing is a world capable of holding on to it long enough for life to dream beside it. By the time the young Earth finally began cooling enough for liquid water to survive on its surface, another mystery had already begun to haunt the planet's future. Where did all that water actually come from? It sounds like a simple question at first. Oceans cover most of Earth. Clouds move endlessly across the sky. Ice hides at the poles and beneath mountains. Water flows so naturally through human life that it feels like part of the planet itself, as if Earth and water were always inseparable. But when scientists started tracing Earth's earliest history backward, the answer became strangely difficult. Because in the beginning, the inner solar system should have been far too hot for large amounts of water to easily survive. Closer to the young sun, temperatures were extreme. The region where Earth formed was violent, unstable, and flooded with energy left over from planetary formation. Many lighter compounds would have struggled to remain intact for long periods. Yet somehow, billions of years later, Earth became a blue world, filled with oceans deeper than mountains are tall. That contradiction forced scientists into a possibility that once sounded almost unbelievable. Maybe Earth's water did not originally belong to Earth at all. Maybe it came from space. The idea began gaining serious attention during the 20th century, especially as astronomers started studying comets more closely. Seen from a distance, comets appear almost ghost-like. Enormous dirty snowballs drifting through darkness with glowing tails stretching millions of miles behind them. But beneath that beauty is something ancient. Many comets are leftovers from the birth of the solar system itself, frozen remnants preserved in distant cold regions where sunlight barely reaches. Some formed so early that they may contain material older than Earth. And inside them is ice, lots of it. Suddenly, a theory emerged that felt both elegant and cinematic at the same time. During the chaotic bombardment phase of the early solar system, countless comets may have crashed into the young Earth over hundreds of millions of years. Each impact could have delivered more ice and water vapor. Slowly, collision after collision, the oceans may have begun accumulating. In this version of the story, Earth's seas are not purely geological features. They are cosmic debris, fragments of ancient frozen objects that wandered through interplanetary darkness before falling onto a molten world. And for a while, the theory seemed almost perfect. But then the chemistry started causing problems. Scientists discovered that not all water is chemically identical. Tiny differences exist in the structure of water molecules depending on how many neutrons hydrogen atoms contain. One important variation involves deuterium, sometimes called heavy hydrogen. By comparing the ratio of deuterium to normal hydrogen inside Earth's oceans with water found in comets, researchers hoped to identify whether comets truly matched Earth's water source. The results became complicated almost immediately. Some comets showed too much deuterium, others appeared closer. A few measurements fit surprisingly well, while many did not. Instead of solving the mystery, each new mission seemed to widen it. The deeper scientists looked, the less the universe behaved cleanly. And then another possibility started becoming harder to ignore. Asteroids. Not the metallic kind often shown in movies, but darker, carbon-rich asteroids filled with primitive minerals. Some of these ancient rocks contain water, chemically trapped inside them. Unlike icy comets from the outer solar system, these objects may have formed closer to Earth's region during planetary formation. That mattered because many of their isotopic signatures looked far more similar to Earth's oceans. Suddenly, the story shifted again. Perhaps Earth's water arrived mainly through impacts, but not from distant comets. Maybe it came from wet asteroids raining down during the solar system's violent youth. Some researchers now believe carbonaceous chondrites, ancient water-bearing meteorites, may represent some of the closest surviving examples of the material that helped seed Earth with water billions of years ago. If true, then the oceans may have begun forming not from giant frozen wanderers alone, but from countless smaller collisions spread across immense spans of time. And yet, even that explanation may still be incomplete, because another unsettling idea slowly emerged beneath both theories. What if Earth already contained water before all those impacts happened? To understand why that possibility matters, you have to picture how planets form. Early Earth was not assembled in one moment. It grew gradually as dust, rock, and planetesimals collided and merged around the young sun. If some of that original material already carried hydrogen and oxygen compounds, portions of future water may have become trapped deep inside the growing planet itself from the very beginning. In other words, Earth may have been born carrying hidden oceans inside its own interior. That possibility once sounded speculative, but discoveries deep beneath Earth's surface began changing the conversation. Volcanoes release enormous amounts of water vapor. Even today, magma rising from Earth's mantle carries dissolved gases upward. Over geological timescales, volcanic activity continuously releases water from deep underground reservoirs into the atmosphere. In the ancient past, when volcanic activity was vastly more intense, those releases may have been enormous. Some researchers now suspect that Earth's early atmosphere could have been built partly from gases vented out of the planet's own interior. Steam accumulated above the surface long before stable oceans existed. Eventually, as Earth cooled enough, that vapor condensed into rainfall, which means some fraction of Earth's oceans may have once been hidden inside molten rock beneath the crust. And the story becomes stranger still. In recent decades, scientists discovered minerals deep within Earth's mantle capable of storing significant amounts of water inside their crystal structures. One mineral in particular, ringwoodite, attracted enormous attention after evidence suggested it could trap water hundreds of kilometers beneath the surface. This does not mean underground caverns full of liquid oceans exist beneath Earth in the way science fiction sometimes imagines. The water is chemically bound within minerals under immense pressure. But the implications are still staggering. There may be enough water hidden deep inside Earth's mantle to rival or exceed the amount in surface oceans. If true, Earth's visible oceans may represent only part of the planet's total water inventory. The rest could still be buried far below us. And suddenly, the original question becomes much harder to answer cleanly. Did Earth's water come from space or from Earth itself? The uncomfortable answer may be both. Modern planetary models increasingly suggest that no single source fully explains Earth's oceans. Some water likely arrived through impacts from asteroids or icy bodies. Some may have existed within the material that formed Earth from the start. Some may have cycled repeatedly between the mantle, atmosphere, and surface over billions of years. Earth's oceans may not have one origin story. They may have several, layered together across deep time. That complexity changes the emotional scale of the mystery. Instead of imagining one dramatic delivery event, you begin seeing Earth as part of a much larger cosmic recycling process. Hydrogen formed shortly after the Big Bang itself. Oxygen emerged later inside stars through nuclear fusion. Ancient stars exploded, scattering heavier elements across space. New solar systems formed from that debris. Planets assembled from ancient dust clouds, already carrying ingredients forged in long-dead stars. Which means the water covering Earth today may contain atoms older than the Sun. Some hydrogen atoms inside modern oceans could have existed from nearly the entire age of the universe. And there is something strangely unsettling about realizing that every glass of water connects directly to cosmic history on that scale. Long before oceans existed, before dinosaurs, before Earth itself, some of those atoms were already drifting through interstellar darkness. But the deeper scientists investigate water's origins, the more another mystery appears underneath everything else. Why did Earth keep its water when so many nearby worlds failed? Mars almost certainly once had rivers, lakes, and perhaps even shallow oceans. Ancient valleys carved across its surface still remain visible today, like scars from a wetter past. But Mars gradually lost much of its atmosphere. Without strong protection, solar wind stripped gases away into space over immense stretches of time. As pressure dropped, liquid water became unstable. Venus may be even more disturbing. Some climate models suggest early Venus might once have possessed shallow oceans billions of years ago. If that is true, then two neighboring planets may have started with significant water supplies. Yet today, one is frozen and barren, the other is a furnace. Earth somehow remained balanced between them, not too hot, not too cold, massive enough to retain atmosphere, yet positioned far enough from the sun to allow stable liquid water over geological timescales. That balance may be far rarer than humans instinctively assume, because water alone is not enough to create oceans. A planet must also keep them, and keeping them may require a chain of conditions so delicate that even small differences can destroy the entire system. A weaker magnetic field, different volcanic chemistry, slight orbital changes, a larger nearby impact. Any one of these might have altered Earth's future permanently, which makes the existence of modern oceans feel less inevitable and more improbable the longer you think about it. The water surrounding human civilization may not simply be a normal planetary feature. It may be the surviving result of billions of years of unstable luck. And somewhere out beyond Earth, hidden among countless stars, there may be worlds that almost became ocean planets, but failed before life ever had a chance to appear. Or perhaps worlds where the oceans arrived, but never stopped boiling. There may have been a moment in Earth's history when the entire planet disappeared behind rain. Not a storm lasting hours, not seasons of heavy clouds, but rainfall so immense, so ancient, and so continuous that it may have reshaped the entire surface of the world over spans of time almost impossible for the human mind to picture. Because once Earth finally cooled enough for water vapor to stop instantly boiling away into space, something extraordinary began happening above the young planet. The sky itself started collapsing. For millions of years before that point, Earth had likely been wrapped in a dense atmosphere filled with superheated steam released by volcanic eruptions, asteroid impacts, and gases trapped deep inside the planet's interior. The surface below remained unstable and violent, rivers of lava cutting across black volcanic plains, while giant impacts still occasionally shattered parts of the crust. But high above that chaos, temperatures slowly continued falling. And eventually, somewhere in the darkness above the early Earth, the first true clouds formed. At first, they may not have resembled modern clouds at all. The atmosphere was radically different from today's world. There was almost no oxygen. Carbon dioxide levels were enormous. Sulfur compounds drifted through the sky. Ash and mineral particles filled the air. Sunlight struggled to penetrate the thick haze surrounding the planet. But as cooling continued, steam condensed. Tiny droplets formed. Then more. Then entire atmospheric systems began changing permanently. And once that process truly started, Earth may have entered one of the longest storms in planetary history. Imagine standing on the surface of that world. The sky is nearly black beneath thick volcanic clouds, glowing faintly orange from lava fields stretching beyond the horizon. Lightning flashes constantly through dense atmospheric layers. Volcanoes erupt in multiple directions at once. The air smells of sulfur, metal, and heated stone. Steam rises everywhere. The ground trembles beneath your feet as parts of the crust shift and crack. Then the rain begins. Not clean rain like modern storms, not cool rain. Scalding water pours from the sky onto a planet still radiating heat from its violent birth. Some researchers believe the first rainfall may have partially evaporated before even reaching the surface in certain regions. In other places, water struck molten rock and exploded instantly back into steam. Earth may have spent enormous periods trapped in a cycle where rain cooled the planet while the planet continuously reheated the atmosphere again. But slowly, almost invisibly at first, the balance started changing. More water remained liquid for longer periods. Pools formed in lower regions. Steam condensed faster than it could fully re-evaporate. And eventually, the first true oceans may have started gathering across Earth's surface. This transition sounds peaceful when compressed into a few sentences, but in reality, it may have been one of the most violent environmental transformations any rocky planet can experience. The early atmosphere likely generated storms beyond anything modern humans have ever seen. Heat escaping from Earth's interior fueled massive atmospheric instability. Without continents shaped like today's world, weather patterns behaved differently. Some models suggest hurricanes may have dwarfed modern storm systems. And yet beneath all that chaos, something essential was happening. The planet was stabilizing. Water was beginning to take control of Earth's future. One reason this period fascinates scientists is because liquid water changes almost everything it touches. Once stable rainfall begins, geology itself transforms. Water breaks down rock. Minerals dissolve and move across landscapes. Temperatures become moderated. Chemical reactions accelerate. Entire planetary systems start behaving differently. Earth was no longer just cooling. It was evolving into something chemically alive. And the rain may have lasted far longer than most people imagine. Not because storms literally never stopped every second for millions of years, but because Earth remained trapped in a long era dominated by condensation, evaporation, volcanic outgassing, and constant atmospheric cycling. Water was moving continuously between sky and surface while the planet struggled toward equilibrium. Some researchers suspect the earliest oceans formed surprisingly quickly once cooling crossed certain thresholds. Others argue the process may have been interrupted repeatedly by catastrophic asteroid impacts capable of reheating parts of the planet again. During the late heavy bombardment, massive collisions still struck Earth frequently enough that some scientists wonder whether portions of the surface oceanized and vaporized multiple times. If that happened, then Earth's first oceans were not stable blue worlds waiting quietly for life. They were temporary survivors inside a planetary battlefield. And the oceans themselves may have looked deeply alien. Modern seawater appears blue largely because of how water absorbs and scatters sunlight. But early Earth's oceans likely contained enormous amounts of dissolved iron and volcanic chemicals. Some scientists believe ancient seas may have appeared dark green, brown, or almost black beneath thick, hazy skies. Sunlight reaching the surface was weaker and heavily filtered through volcanic gases. The moon orbited much closer to Earth than it does today, appearing dramatically larger in the sky and generating stronger tides across unstable coastlines. Even the rain itself may have been chemically aggressive. Without modern atmospheric oxygen, early rainwater interacted differently with gases in the atmosphere. Carbon dioxide dissolved into water, creating acidic conditions. Sulfur compounds from volcanic eruptions likely intensified that effect further. In some regions, rain may have resembled diluted acid storms more than anything humans experience today. And still, against all appearances, these hostile oceans may have prepared the planet for life. That is one of the strangest parts of Earth's history. The environments that seem most terrifying to human imagination may have been exactly the conditions needed for biology to emerge. Because water does more than simply exist. Water carries. It transports minerals, heat, and chemicals across vast distances. It creates environments where molecules collide, combine, separate, and reorganize. Once oceans formed, Earth became a gigantic chemical laboratory, operating continuously across the entire planet. Lightning struck atmospheric gases. Minerals dissolved into seawater. Volcanic vents released metals and heated fluids from deep underground. Meteorites delivered additional organic compounds from space. And somewhere inside all this chaos, chemistry may have started crossing a boundary that had never existed before. The boundary between non-living matter and life. No one knows exactly where that happened. Some theories place the origin of life in shallow tidal pools repeatedly flooded and dried by ancient tides. Others focus on hydrothermal vents deep beneath the oceans, where heated, mineral-rich water erupted from Earth's crust. In those dark environments, strange ecosystems still survive today, without sunlight, feeding entirely on chemical energy. The existence of those modern deep-sea ecosystems changed scientific thinking dramatically. Before their discovery, many researchers assumed sunlight was absolutely necessary for complex biological systems. But hydrothermal vents revealed something unsettling. Life can thrive in darkness. That realization reopened the possibility that Earth's earliest organisms may have emerged far below the surface, hidden beneath violent storms and toxic skies, while the planet above remained hostile. And there is another eerie implication hidden inside that idea. If life began underground or deep underwater, then Earth's first living systems may have survived catastrophic asteroid impacts that repeatedly sterilized parts of the surface. Entire oceans may have boiled in some regions, while microbial ecosystems continued surviving far below, protected by rock and water. Life on Earth may have endured apocalypse before complex organisms even existed. The more scientists study this period, the more Earth's early history stops resembling a simple progression and starts feeling like survival against impossible odds. Because none of this was guaranteed. Water could have escaped into space. The atmosphere could have collapsed. The planet could have overheated permanently, like Venus. Large impacts could have repeatedly delayed stable oceans for far longer than they actually did. And yet somehow, the cycle held together. Rain continued falling. Oceans deepened. The crust cooled further. The atmosphere slowly transformed. And over immense stretches of time, Earth crossed a threshold that may be extremely rare in the universe. A rocky planet maintaining long-term, stable liquid water at its surface. That phrase sounds technical at first, but its meaning is profound. Stable liquid water means memory. Rivers can carve landscapes. Chemistry can accumulate complexity. Climate can stabilize. life can persist long enough to evolve. Without long-term water stability, planets remain geologically interesting, but biologically silent. And perhaps that is why Earth's ancient rainfall matters so much. Those storms did not merely fill oceans. They may have created the first continuous bridge between geology and biology in planetary history. Every future forest, animal, civilization, and human story depended on those early cycles continuing long enough for life to gain a foothold. And even now, billions of years later, Earth is still living inside the same ancient system born during that distant era. Water still rises into clouds. Clouds still collapse into rain. Rivers still carry minerals toward the sea. Oceans still regulate the climate of the planet. The cycle never truly ended. It only became calmer. But perhaps the most haunting thought comes from imagining how this same process may be unfolding elsewhere right now. Somewhere beyond Earth, another young planet may currently be hidden beneath colossal storms. Steam clouds may be condensing over molten landscapes beneath alien skies. Oceans may be forming for the first time in darkness no human will ever see. And on that distant world, rain may already be preparing another planet for life, long before anything living exists to witness it. From space, Earth does not immediately look rare. That may be the strangest part of the story. Clouds swirl across its atmosphere. White ice stretches over the poles. Oceans reflect sunlight back into darkness. From a distance, it feels natural, almost expected, that a planet would look this way. Humans grow up surrounded by rivers, rain, lakes, and seas. So water begins to feel ordinary, permanent, almost guaranteed. But the deeper scientists explore the solar system, the more unsettling the truth becomes. Water is not the rare thing. Stable oceans are. Because once researchers started searching beyond Earth, they discovered traces of water almost everywhere. Ice hides inside shadowed craters on Mercury. Frozen reservoirs exist beneath the dusty surface of Mars. Massive underground oceans may lie beneath the icy crusts of Europa and Enceladus. Saturn's moon Titan has rivers and lakes, though they are made mostly of liquid methane rather than water. Even comets drifting through deep space carry enormous amounts of ice. The universe seems surprisingly willing to create water. And yet, despite all of that, Earth remains the only known world with vast liquid oceans exposed openly on its surface. That distinction changes everything. Because having water somewhere is not the same as maintaining a living ocean world for billions of years. To understand how unusual Earth may be, you have to look at the planets surrounding it, almost like failed experiments. Mars is perhaps the most haunting example. Today, Mars looks cold, silent, and empty. Dust storms sweep across dry plains beneath a thin, pink sky. Temperatures collapse far below freezing. Most liquid water instantly evaporates or freezes under the weak atmospheric pressure. But ancient Mars was different. Orbiters and rovers have revealed dried river valleys, lake beds, mineral deposits, and erosion patterns that strongly suggest water once flowed across large parts of the planet. Some regions may have contained lakes lasting millions of years, perhaps even shallow seas. And if you could travel back far enough into Mars's distant past, the planet might not have looked entirely alien. It may have had clouds, rain, rivers cutting through rock, and snow falling across ancient volcanic landscapes. So what happened? That question still haunts planetary science, because Mars seems to represent a world that almost became Earth-like, but failed somewhere along the way. Part of the problem was size. Mars is much smaller than Earth, and smaller planets cool faster internally. Over time, its core lost much of the heat needed to sustain a strong magnetic field. Without that invisible shield, solar wind from the sun gradually stripped away much of the Martian atmosphere. As atmospheric pressure weakened, stable liquid water became harder and harder to maintain. The oceans did not necessarily disappear all at once. They may have slowly faded, evaporating, freezing underground, escaping into space molecule by molecule across billions of years. And there is something deeply eerie about that process, because Mars shows how a planet can lose habitability without exploding dramatically. It can simply decline into silence, one atmosphere at a time. But if Mars feels tragic, Venus feels terrifying. Venus is often called Earth's twin because the two planets are remarkably similar in size and composition. At first glance, they should have evolved somewhat alike. Yet Venus became one of the most hostile places in the solar system. Surface temperatures are hot enough to melt lead. Atmospheric pressure is crushing. Thick clouds of sulfuric acid cover the planet permanently. And beneath those clouds lies one of the biggest mysteries in planetary history. Some climate models suggest Venus may once have possessed significant amounts of water, possibly oceans. Not everyone agrees on how long those oceans could have survived, and the evidence remains debated. But if early Venus truly had liquid water, then the implications are disturbing. It means two neighboring planets may have started with many similar ingredients: rocky surfaces, atmospheres, volcanic activity, water sources, yet ended with radically different destinies. Somewhere in Venus's past, the balance broke. As the sun gradually brightened over time, temperatures may have increased enough to accelerate evaporation. More water vapor entered the atmosphere. Water vapor itself is a powerful greenhouse gas, trapping additional heat. More heat caused more evaporation. The cycle intensified until the oceans eventually vanished into the atmosphere entirely. This process is sometimes called a runaway greenhouse effect, and once it fully begins, reversing it may become almost impossible. Ultraviolet radiation from the sun likely split water molecules high in Venus's atmosphere. Hydrogen escaped into space. Oxygen reacted with surface materials. Slowly, the planet lost its water forever. Venus became a warning written across an entire world. A planet can begin with water and still lose everything. Earth somehow avoided that fate. And the deeper scientists study the difference, the stranger Earth begins to seem. Part of the answer lies in distance. Earth orbits within what astronomers often call the habitable zone, the region around a star where temperatures may allow liquid water to exist on a planet's surface. Too close to the sun, water evaporates uncontrollably. Too far away, it freezes permanently. But the habitable zone is not a magical guarantee. It is more like a narrow opportunity. And Earth occupies that opportunity with unsettling precision. A slightly different orbit could have changed everything. Even small shifts in average temperature across geological timescales can dramatically alter planetary climate systems. Earth benefits not only from its distance, but also from a complex combination of stabilizing processes working together continuously. One of the most important may be the magnetic field generated deep inside Earth's core. You cannot see it directly, but it stretches far into space around the planet like an invisible shield. When charged particles from the sun strike Earth, much of that energy is deflected away. Without this protection, atmospheric erosion could become far more severe over immense periods of time. Mars lost most of its magnetic protection long ago. Earth kept theirs, and that single difference may have helped preserve oceans for billions of years. Then there is plate tectonics, another process that may be more important than humans usually realize. Earth's crust is broken into massive moving plates, slowly shifting across the planet's surface. This movement recycles carbon between the atmosphere, oceans, and interior through volcanic activity, erosion, and subduction. Over geological timescales, this acts almost like a planetary thermostat, helping regulate climate. Too much carbon dioxide in the atmosphere increases warming, but weathering and ocean chemistry gradually remove some of it. Volcanic activity later returns carbon back into the system. It is not perfectly balanced, but it creates long-term stability unusual among rocky worlds. Earth does not simply possess oceans. The planet actively helps maintain them. And this may be one reason why finding truly Earth-like worlds elsewhere could be much harder than simply finding water. Because habitability may depend on multiple fragile systems functioning together simultaneously for immense stretches of time. The right star, the right orbit, the right planetary mass, a stable atmosphere, magnetic protection, long-term geological activity, chemical cycles capable of preventing climate collapse. Remove enough pieces from that chain and oceans disappear, sometimes gradually, sometimes catastrophically. Yet even beyond Earth, there are worlds that complicate the story further. Europa, one of Jupiter's moons, likely contains a massive ocean hidden beneath thick ice. Some estimates suggest it may hold more water than all of Earth's oceans combined. Enceladus ejects giant plumes of water vapor from beneath its frozen crust into space. These discoveries changed scientific thinking because they revealed that liquid water environments may exist far beyond traditional habitable zones. But these worlds also reveal something important. Liquid water alone is not enough to create an Earth. Europa's ocean is buried beneath kilometers of ice in perpetual darkness. Enceladus is frozen at the surface. Titan's rivers flow not with water, but methane and ethane under temperatures cold enough to freeze solid almost everything humans associate with life. Earth's oceans remain unusual because they are open to the atmosphere, connected to weather systems, sunlight, climate cycles, and continental chemistry all at once. The planet exists in a delicate middle state between freezing and boiling, and perhaps that middle state is one of the rarest conditions in the universe. There is also a deeper emotional weight hidden inside this realization. Humans often imagine Earth as stable because civilizations rise and fall over timescales tiny compared to planetary history. Oceans seem eternal when measured against human lifetimes. But from a cosmic perspective, Earth's habitability may actually be temporary. The sun grows slightly brighter over time. Continents shift. Atmospheres evolve. Climate systems change. Billions of years from now, Earth itself may eventually lose the stable conditions that allowed oceans to survive this long, which means the blue planet humans know today may represent a narrow window in time rather than a permanent state, a rare balance that happened to last long enough for intelligent life to emerge and notice it. And perhaps that is what makes Earth feel so strange the more you think about it. Not because water exists here, but because everything aligned just well enough for oceans to remain alive beneath an open sky for billions of years without vanishing into ice, steam, or darkness. A planet balanced carefully between silence and survival. Long before Earth had forests, animals, or even breathable air, the oceans were already busy experimenting. That may sound like poetry at first, but in a strange way, it is also chemically true. Because once stable water covered parts of the young Earth, the planet stopped being only a world of rock and heat. It became something far more unpredictable, a place where molecules could move, collide, combine, separate, and reorganize endlessly across enormous stretches of time. And somewhere inside that restless chemical chaos, something crossed a line that had never been crossed before. Matter began trying to stay alive. No one knows the exact moment it happened. There are no fossils recording the birth of the first living thing. The oldest direct traces of life are already surprisingly sophisticated, suggesting biology may have started much earlier than the evidence we currently possess. Some scientists suspect life emerged remarkably fast once Earth's oceans stabilized. Others believe the transition from chemistry to biology may have taken hundreds of millions of years filled with failed experiments. Either way, water appears at the center of nearly every serious explanation. Because life did not simply appear on Earth, it emerged inside water. And the deeper scientists study the chemistry of living systems, the stranger that connection becomes. Every known organism depends on water at a fundamental level. Cells are mostly water. Blood is water-rich. Oceans regulate climate. Even DNA, the molecule carrying genetic information, behaves the way it does, partly because of water surrounding it. Remove water from biology, and the machinery of life begins collapsing almost immediately. That dependence raises an unsettling possibility. Perhaps life and liquid water are not separate phenomena at all. Perhaps water was the environment that made life physically possible from the beginning. To understand why, You have to imagine the early oceans not as peaceful blue seas, but as gigantic chemical worlds filled with instability. Volcanoes continuously released gases and minerals into the atmosphere and oceans. Lightning struck through dense clouds rich in carbon compounds. Meteorites carried additional organic molecules from space. Hydrothermal vents pumped heated, mineral-rich fluids from deep inside Earth's crust into seawater. The planet was chemically active everywhere, and water connected all of it. That connection matters because water is an unusually powerful solvent. It dissolves enormous numbers of substances, allowing molecules to move freely and interact constantly. In dry environments, chemistry can become limited and static. But inside water, molecules drift, collide, break apart, and recombine continuously. The early oceans were not passive scenery. They were giant reaction chambers operating across an entire planet. One of the most famous attempts to recreate those ancient conditions came in 1953 through the Miller-Urey experiment. Scientists built a sealed system containing gases thought to resemble Earth's early atmosphere and added electrical sparks to simulate lightning. After running the experiment, they discovered amino acids. Some of the basic building blocks of proteins had formed naturally. The experiment did not create life, but it revealed something deeply important. Complex organic molecules may emerge surprisingly easily under the right conditions. That realization changed science permanently because it suggested biology might not require a miraculous event in the traditional sense. Chemistry itself may naturally drift toward complexity when energy, water, and the right ingredients interact long enough. Still, creating amino acids is one thing. Creating life is something else entirely. A living system must do more than exist chemically. It must store information, maintain structure, reproduce, and adapt. Somewhere during Earth's early history, chemistry crossed from simple reactions into organized, self-sustaining systems. And scientists still do not fully understand how that leap happened. One major idea is known as the RNA world hypothesis. Today, DNA stores genetic information, while proteins perform many biological tasks. But RNA is different. It can both carry information and assist certain chemical reactions. Some researchers suspect early life may have relied primarily on RNA before DNA-based life evolved later. In this scenario, Earth's oceans may have contained countless short-lived molecular chains forming and breaking apart continuously. Most disappeared immediately, but eventually, purely through chemistry and time, some structures may have become better at reproducing themselves. Not alive in the modern sense, not conscious, not even cells yet, but systems capable of persistence. And once self-replication begins, evolution enters the story. Because from that point forward, successful molecules survive longer and spread more effectively than unstable ones. Chemistry stops being random and begins selecting. The strange thing is that this process may have happened many times before anything durable emerged. Some scientists suspect early Earth may have produced countless primitive biological experiments that vanished completely. Entire branches of pre-life chemistry could have risen and disappeared before the ancestors of modern life finally gained stability. If true, then Earth's oceans may once have been filled with forms of proto-life now erased so completely that no trace remains. That possibility changes the emotional tone of Earth's origin story. Instead of imagining life appearing instantly in one dramatic moment, you begin seeing the early oceans as a place of endless chemical trial and error, stretching across immense periods of time. And water sat underneath all of it. But perhaps the most fascinating theories place the origin of life far from sunlight entirely. Deep beneath the ancient oceans, hydrothermal vents release heated water rich in minerals from Earth's interior. Around some of these vents today, bizarre ecosystems thrive in complete darkness. Giant tube worms, microbes, and strange crustaceans survive without depending directly on sunlight at all. Instead, they feed on chemical energy rising from the planet itself. When scientists first discovered these ecosystems in the late 20th century, it shocked biology. Life did not need sunlight nearly as absolutely as many researchers had assumed. That discovery reopened an extraordinary possibility. Maybe life began not in shallow, warm ponds beneath lightning-filled skies, but deep underwater, near volcanic vents hidden beneath the oceans. Those environments offer several advantages. Mineral-rich fluids create strong chemical gradients capable of driving complex reactions. Rock surfaces provide microscopic compartments where molecules can concentrate rather than drifting endlessly through open water. Heat from Earth's interior supplies constant energy. And deep underwater environments offer protection from asteroid impacts and harsh ultraviolet radiation that bombarded the early surface. In some ways, hydrothermal vents resemble tiny worlds powered from below rather than above. And if life truly began there, then the first living systems on Earth may have emerged in darkness long before the atmosphere became stable enough for complex surface ecosystems. There is something unsettling about imagining that. The ancestors of every tree, whale, bird, and human being may trace back not to sunlight or open skies, but to black volcanic water hidden miles beneath ancient oceans. And even now, deep beneath the sea, those environments still exist, almost unchanged. Ancient worlds surviving inside the modern planet. But water may have done something even more important than simply allowing chemistry to happen. It may have slowed Earth down. Water absorbs and stores heat extraordinarily well. Oceans regulate climate, distribute energy around the planet, and prevent temperature extremes from becoming too unstable. Without large bodies of water, Earth may have experienced far more violent climate swings during its early history. Life needs time, and oceans may have provided it. Because biological complexity does not emerge instantly, it requires long periods where environments remain stable enough for fragile systems to persist, evolve, and adapt. Water softens some of Earth's chaos, just enough for evolution to keep moving forward instead of repeatedly resetting. The irony is that early life itself may have transformed the oceans in return. The first microorganisms likely lived in an atmosphere almost completely lacking oxygen. Many early organisms may even have considered oxygen toxic. But over immense stretches of time, photosynthetic microbes began releasing oxygen into the oceans and atmosphere as waste. At first, the oxygen reacted with dissolved iron in seawater, creating massive mineral deposits that still exist today. Entire oceans slowly changed chemistry. Eventually, oxygen began accumulating in the atmosphere itself. The planet transformed again. And this time, life was helping drive the transformation. Earth's oceans were no longer simply the setting for biology. They had become part of a feedback loop between geology, climate, chemistry, and living systems. A living planet was emerging. And perhaps the strangest part of all this is realizing how thin the boundary between lifeless chemistry and biology may actually be. Scientists still cannot point to one exact moment where non-living matter officially became alive. The transition appears gradual, blurry, and deeply complex, which raises uncomfortable questions. If life emerged relatively naturally on Earth once water stabilized, then perhaps biology is common throughout the universe. But if Earth required an extremely rare chain of conditions, precise chemistry, stable oceans, geological energy, atmospheric protection, and immense stretches of uninterrupted time, then intelligent life may be extraordinarily uncommon. Right now, no one knows which possibility is true, and that uncertainty changes the meaning of water entirely. Because oceans may not just represent habitability, they may represent opportunity. Somewhere beneath the waves of the ancient Earth, molecules once drifted together long enough to begin remembering themselves. That memory slowly evolved into cells, ecosystems, consciousness, civilizations, and eventually humans, capable of questioning where life began in the first place. And all of it may trace back to a planet that reigned for millions of years until chemistry finally learned how to survive inside the sea. If you could travel backward through Earth's history far enough, the map of the planet would eventually stop making sense. The Atlantic Ocean would vanish. North America and Africa would begin sliding together. India would drift far from Asia. Entire coastlines familiar to human civilization would disappear beneath alien seas or rise upward into mountain ranges that did not yet exist. And then, if you kept going deeper into the past, even the oceans themselves would start disappearing. Not drying up, not evaporating into the sky, but physically ceasing to exist as Earth slowly rearranged its surface over hundreds of millions of years. Because one of the strangest truths about our planet is that oceans are not permanent features. They are temporary. Even the largest seas on Earth are only brief chapters in a much longer planetary story. Right now, humans look at the Pacific Ocean and instinctively imagine permanence. It stretches across nearly half the planet. Entire civilizations depend on it. Storm systems, climate patterns, ecosystems, and global trade all move through its waters. From a human perspective, it feels eternal. But in geological time, even the Pacific is already dying. Very slowly, almost invisibly, Earth is recycling it. That process begins deep beneath the ocean floor itself. The surface of Earth is broken into massive tectonic plates that drift slowly across the planet over immense stretches of time. These movements are usually measured in centimeters per year, about as fast as fingernails grow. Yet, given enough millions of years, continents collide, oceans open, and entire planetary landscapes vanish. Where tectonic plates pull apart, new ocean floor forms from rising magma. Where plates collide, one section of crust can sink beneath another in a process called subduction. And when oceanic crust sinks back into Earth's mantle, parts of the ocean effectively begin disappearing underground. This means Earth's oceans are not static pools of water resting on an unchanging surface. They are part of a gigantic planetary recycling system. The seafloor itself is constantly being destroyed and rebuilt, and some ancient oceans have already been erased so completely that humans only know they existed because fragments remain trapped inside rocks and mountain ranges. One of the greatest lost oceans in Earth's history was Panthalassa. Around 250 million years ago, nearly all of Earth's continents were joined together into the supercontinent Pangaea. Surrounding that enormous landmass stretched a vast global ocean so immense it covered most of the planet. That ocean was Panthalassa. Imagine standing on the shores of that ancient sea. There are no modern continents, no Atlantic Ocean, no familiar coastlines. Strange early reptiles move across barren landscapes, while gigantic storms form over waters stretching almost endlessly beyond the horizon. The moon hangs over a world that feels both ancient and unfinished. Panthalassa dominated the planet for millions of years, and yet today, almost none of it survives. Most of its ocean floor has been consumed back into Earth's mantle through subduction. Unlike continental crust, which can survive billions of years, oceanic crust is relatively young because Earth continuously recycles it. Very little seafloor older than about 200 million years still exists today, which creates a strange problem for scientists. The largest parts of Earth's ocean history are gone, destroyed beneath the planet itself. Researchers reconstruct those vanished oceans almost like detectives rebuilding a lost world from fragments. Magnetic patterns frozen into rocks reveal how tectonic plates moved. Fossils appear in places where ancient seas once existed. Mountain ranges sometimes contain marine sediments lifted thousands of feet above sea level, proving those rocks once rested beneath oceans long vanished. Earth hides its own past beneath continents. Another lost ocean, the Tethys Sea, shaped huge portions of the ancient world before disappearing almost entirely. Hundreds of millions of years ago, the Tethys stretched between massive continental plates separating what would later become Africa, Europe, and Asia. Marine reptiles swam through warm, shallow waters while coral reefs expanded beneath tropical skies. Entire ecosystems flourished there long before humans existed. But tectonic motion never stopped. As Africa and India drifted northward, the Tethys slowly began closing. Its seafloor sank beneath colliding continents. Sediments compressed upward into mountain ranges. The Himalayas themselves, the tallest mountains on Earth, still contain marine fossils from the vanished Tethys Ocean trapped high above the clouds. Which means parts of Mount Everest were once underwater. That idea feels almost impossible the first time you hear it. Marine life once existed where climbers now struggle to breathe. And that transformation reveals something unsettling about Earth itself. The boundary between ocean and land is not permanent. Over geological time, entire worlds trade places. Sea becomes mountain. Continents split apart. Oceans open and close repeatedly, like enormous planetary lungs breathing across hundreds of millions of years. But some missing oceans may be even stranger than the ones visible in the rock record, because scientists now suspect that enormous amounts of Earth's water may have disappeared deep underground. Not into caves, not into hidden reservoirs humans could ever reach, but into Earth's mantle itself. Water travels downward when tectonic plates carrying oceanic crust sink beneath continents or other plates. Minerals within the crust can trap water chemically inside their structures. As subduction continues, portions of that water descend far into Earth's interior. For decades, researchers debated how much water Earth's mantle might actually contain. Then, discoveries involving deep mantle minerals began changing the scale of the discussion entirely. One mineral in particular, ringwoodite, became especially important. Under the immense pressures found deep beneath Earth's surface, ringwoodite can hold significant amounts of water locked inside its crystal structure. Evidence from deep mantle samples suggests water may exist throughout huge regions of Earth's interior in chemically bound form. Not underground oceans in the human sense, but something perhaps even stranger. A hidden planetary reservoir spread through rock itself. Some estimates suggest the mantle could contain amounts of water comparable to multiple surface oceans combined. If true, then Earth's visible seas may represent only a fraction of the planet's total water. The rest may be cycling slowly through the deep interior over billions of years. That possibility changes how you imagine the oceans entirely. The seas covering Earth's surface are not isolated features. They may be temporary expressions of a much deeper planetary water cycle connecting atmosphere, crust, mantle, and volcanic systems together across immense spans of time. And volcanoes may be one of the visible clues. When volcanoes erupt, they release gases from Earth's interior, including water vapor. Some of the water inside modern oceans may once have been buried deep underground before returning to the surface through volcanic activity. Likewise, some water currently at the surface may eventually sink back into the mantle again. Earth is not simply holding oceans, it is circulating them through the planet itself. Slowly, relentlessly, over billions of years. And there is another unsettling implication hidden inside this cycle. Earth may have lost oceans before, in ways humans would barely recognize. During certain ancient climate extremes, global ocean chemistry changed dramatically. At times, oceans may have become depleted of oxygen over enormous regions. Some extinction events were linked to catastrophic disruptions in marine systems triggered by volcanic eruptions, climate shifts, or rapid carbon release. there were periods when Earth's oceans became hostile to much of complex life. Dark, stagnant, toxic. The seas remained physically present, but biologically, they transformed into something closer to alien environments. One example occurred during the Permian-Triassic extinction around 252 million years ago, the worst mass extinction in Earth's history. Massive volcanic eruptions likely destabilized climate systems and ocean chemistry on a global scale. Oxygen levels in parts of the oceans collapsed. Many marine ecosystems died out almost completely. More than 90% of marine species may have disappeared. Earth's oceans survived physically, but the living worlds inside them nearly vanished. And perhaps that is one reason ancient oceans feel so haunting to scientists. Oceans are often imagined as symbols of stability, yet Earth's history shows they can transform radically. Seas rise and fall. Currents change. Entire ecosystems collapse and reappear. The modern oceans humans know are not the permanent default state of the planet. They are the latest version, and eventually, they too will change beyond recognition. The Atlantic Ocean itself is relatively young in geological terms, opening as Pangaea slowly split apart. The Pacific, despite its enormous size, is shrinking because tectonic plates around its edges continue consuming oceanic crust. Millions of years from now, new supercontinents may form. Familiar oceans may close permanently, while entirely new seas emerge elsewhere. Future Earth may look unrecognizable to us. And somewhere inside all this movement is a deeper realization about the nature of planets themselves. Earth is not a finished world. It is still evolving. The continents humans stand on today are temporary arrangements drifting across a restless surface above a hot interior that never fully stopped moving. Oceans appear eternal only because human history is too short to watch them vanish. But the planet remembers. Deep inside mountain ranges, buried sediments, magnetic minerals, and ancient crystals, Earth still carries the remains of seas that disappeared hundreds of millions of years before humans existed. Ghost oceans hidden inside stone. And perhaps the strangest thought of all is that some water from those vanished oceans may still exist today. Not in the sea, but deep beneath your feet, locked inside Earth itself, waiting for another cycle to someday return it back to the surface again. At first, humans believed water belonged mainly to Earth. It filled our oceans, shaped our weather, carved canyons through mountains, and drifted endlessly through clouds above civilization. For most of history, water felt deeply tied to this planet, almost like part of Earth's identity itself. But the deeper science pushed outward into the solar system and beyond, the stranger the universe became. Because water kept appearing in places where it almost seemed impossible, hidden beneath frozen wastelands, floating through interstellar darkness, locked inside minerals buried deep underground, suspended near black holes, falling sideways across alien worlds, beneath skies no human being will ever stand beneath. And with every discovery, one unsettling idea grew harder to ignore. Perhaps water is not unusual at all. Perhaps the universe is filled with it. The real mystery may be why some forms of water become oceans, weather systems, ecosystems, and eventually living worlds, while most remain trapped inside environments so hostile that life, at least as humans understand it, may never survive there. One of the strangest examples exists far beneath Antarctica. From above, Antarctica looks silent and frozen beyond imagination, a continent buried beneath miles of ice and darkness for millions of years. Temperatures collapse far below freezing. Winds sweep across empty white plains with almost no visible life. Yet, hidden underneath that ice are entire lakes that should not exist. One of them is Lake Vostok. Buried beneath more than 2 miles of ice, this enormous subglacial lake remained sealed off from Earth's atmosphere for possibly millions of years. No sunlight reaches it. The pressure is immense. The environment is isolated almost beyond comprehension. And yet, liquid water survives there. The heat rising slowly from Earth's interior, combined with the insulating effect of thick ice above, prevents the lake from freezing solid. Scientists believe similar hidden lakes may exist throughout Antarctica, forming an invisible world trapped beneath the frozen surface. There is something deeply eerie about imagining dark liquid water hidden under endless ice for geological ages, an isolated world beneath another world. And discoveries like that changed how scientists think about habitability elsewhere. Because if liquid water can survive beneath Antarctic ice, then maybe frozen worlds in space are not truly dead either. That realization transformed the importance of Europa almost overnight. Europa, one of Jupiter's moons, appears at first glance like a frozen sphere cracked by enormous lines stretching across its icy surface. Temperatures there are unimaginably cold. Radiation from Jupiter bombards the moon constantly. Sunlight is weak. The surface looks lifeless. But beneath that ice, scientists strongly suspect a massive ocean exists. Not a small underground sea, an ocean potentially deeper than all of Earth's oceans combined. Tidal forces generated by Jupiter's gravity flex Europa's interior continuously, creating heat beneath the frozen crust. That heat may keep a global ocean liquid far below the surface. Some estimates suggest the ocean could contain more than twice as much water as Earth. And suddenly, the imagination begins drifting into unsettling territory. A hidden ocean larger than Earth's beneath permanent darkness. No skies, no continents, no sunlight reaching the water above. Only black, pressure-filled depths stretching endlessly under ice. If life exists there, it may have evolved completely separated from the kind of environments humans instinctively associate with biology. And Europa is not alone. Saturn's moon Enceladus became even more shocking after spacecraft observed giant plumes erupting from cracks near its south pole. These plumes contain water vapor, ice particles, salts, and organic compounds blasting into space from an underground ocean hidden beneath the moon's icy shell. The more scientists studied those eruptions, the stranger the chemistry appeared. Some evidence even hinted at hydrothermal activity on the ocean floor beneath the ice. In other words, Enceladus may contain liquid water, internal heat, minerals, and chemical energy sources, all existing together in one hidden environment. The same ingredients many researchers consider important for life on Earth. Which means, somewhere beneath the frozen crust of a moon orbiting Saturn, there may be dark oceans chemically active enough to support biology. No one knows for certain, but the possibility alone changed how humans think about life in the universe. Because suddenly, Earth no longer looked like the only place where oceans could exist. Just the only one where oceans exist openly beneath the sky. Then there is Titan, perhaps one of the most alien, yet strangely familiar worlds ever discovered. Titan has rivers, lakes, rainfall, clouds, weather systems. At first glance, it almost resembles a colder version of Earth. But the liquid flowing across Titan's surface is not water. It is methane and ethane. Temperatures there are so cold that water behaves almost like rock. Ice forms mountains harder than stone. Meanwhile, methane cycles through the atmosphere the way water does on Earth, evaporating, condensing into clouds, and falling as rain. Titan reveals something deeply strange about planetary systems. Under different temperatures and pressures, entirely different liquids can take over the role water plays on Earth. And that realization widens the imagination dramatically. Perhaps Earth-like oceans are only one version of what a living planetary cycle can look like. But the universe becomes even stranger once you leave planets behind entirely. Because water exists in interstellar space too. Astronomers have discovered enormous clouds of water vapor drifting through distant regions of the galaxy. Some of these reservoirs are almost incomprehensibly large. One massive cloud surrounding a distant quasar contains enough water to fill Earth's oceans trillions of times over. The scale barely feels real. Water floating across deep space around one of the most violent objects in the universe. And that contrast is what makes the discovery feel so unsettling. Quasars are powered by supermassive black holes consuming matter at enormous rates. Radiation pouring from these systems can outshine entire galaxies. Yet somehow, even in those extreme environments, water molecules still form and survive. Which means water is not confined to peaceful planets. The universe creates it in places humans would never intuitively expect. Near black holes, inside collapsing gas clouds, around dying stars, within frozen comets drifting between planets. And perhaps most strangely of all, astronomers now suspect some exoplanets may be almost entirely covered by oceans. These so-called water worlds may contain global seas hundreds or even thousands of miles deep, with no continents rising above the surface at all. In some models, pressure deep within those oceans becomes so extreme that exotic forms of ice may exist beneath liquid layers, despite enormous temperatures. Imagine a planet where no land exists anywhere. No beaches, no mountains breaking the horizon. Only endless ocean stretching around the entire world beneath alien skies. If life emerged there, it would evolve without ever knowing solid ground. And somewhere in all these discoveries, humans began realizing something profound. Water itself may be incredibly common, but Earth's version of water may not be, because liquid oceans exposed at the surface under stable atmospheric conditions appear surprisingly delicate when compared to the universe as a whole. Most water exists frozen, buried, chemically trapped, or floating through hostile environments. Earth's oceans remain unusual because they sit inside a narrow balance where temperature, pressure, atmosphere, gravity, and geology all cooperate long enough for complexity to emerge. And even on Earth, water still hides in places that feel almost impossible. Deep underground caves isolated for millions of years. Tiny droplets trapped inside ancient crystals older than multicellular life. Superheated water near volcanic vents where temperatures should theoretically destroy stable ecosystems. Microbial communities surviving inside Antarctic ice. Water continues appearing in places where life itself seems unlikely. Sometimes it feels less like a substance and more like a persistent force threading through the universe in every direction possible. And perhaps the most unsettling thought comes from realizing humans still do not know how many hidden oceans remain undiscovered. There may be underground seas beneath distant moons not yet explored. Water-rich planets may orbit stars humans have barely studied. Entire ecosystems could exist beneath ice layers so thick that sunlight never reaches them. Some scientists even speculate that rogue planets drifting through interstellar space without stars might maintain hidden subsurface oceans through internal heat alone. Dark worlds wandering endlessly through space with buried seas no one will ever see. That possibility changes the emotional scale of the universe. Because once humans understood water only as part of Earth. Now it appears woven into cosmic history itself. From underground Antarctic lakes to oceans beneath alien moons. From storms of methane on Titan to water vapor near black holes. The universe keeps revealing the same unsettling pattern over and over again. Water finds a way to exist almost everywhere. But worlds capable of turning that water into life, memory, civilizations, and consciousness may be far rarer than humans once imagined. And somewhere out there tonight, hidden beneath ice or drifting through darkness, another ocean may already exist, with no living thing yet aware of it. At first glance, water looks almost too ordinary to deserve much attention. It falls from the sky. It fills sinks and rivers. It freezes into ice cubes and disappears into steam. Humans touch it every day without thinking. Entire civilizations have treated water mainly as a resource, something to drink, transport, store, or fight over. But the deeper scientists studied it, the stranger it became. Because water behaves in ways it probably should not. And if even a few of those behaviors were slightly different, Earth might never have become a living world at all. That realization begins with something deceptively simple. Most substances become denser when they freeze. Water does the opposite. When liquid water cools into ice, its molecules arrange themselves into structures that actually take up more space. The frozen form becomes less dense than the liquid beneath it. That is why ice floats. Humans learn this so early that it feels obvious. But from a physics perspective, it is deeply unusual, and the consequences are enormous. Imagine if ice behaved like most substances and sank instead. Every winter, frozen water would drop beneath lakes and oceans rather than forming insulating layers at the surface. Over time, more ice would accumulate below. Entire bodies of water could freeze progressively downward. In extreme climates, oceans might eventually become solid from the bottom up. Instead, floating ice creates protection. Once a frozen layer forms at the surface, it slows further heat loss from the water below. Liquid environments can continue surviving beneath ice even during brutal cold periods. Fish survive winter because of this. Entire ecosystems persist because of this. And during ancient climate catastrophes, this property may have helped keep Earth's oceans from freezing completely. One strange molecular behavior may have protected the continuity of life across geological ages. The deeper you look, the less water resembles an ordinary liquid, and the more it begins feeling like something balanced on improbable rules. Take temperature. Water absorbs enormous amounts of heat before changing temperature significantly. Scientists call this high specific heat capacity. But the effect is easier to understand emotionally than technically. Oceans act like giant planetary batteries for heat. During summer, they absorb energy slowly. During winter, they release it gradually back into the atmosphere. Coastal regions remain more stable because nearby water moderates extreme temperature swings. Ocean currents redistribute heat across the planet, shaping climate systems on continental scales. Without this property, Earth's weather would likely become far more violent and unstable. Days could become hotter, nights colder, seasonal extremes more severe. The climate systems supporting long-term biological stability might never have remained predictable enough for complex ecosystems to flourish. And perhaps most importantly, early Earth itself may have become too chaotic for life to evolve consistently. Water softened the planet, not emotionally, physically. It stabilized temperatures long enough for biological complexity to slowly emerge, rather than repeatedly collapsing under environmental extremes. But water's strange behavior continues even deeper into chemistry itself. Water molecules are polar, meaning one side carries a slightly positive charge, while the other carries a slightly negative one. This creates weak attractions between neighboring molecules known as hydrogen bonds. Those bonds are responsible for many of water's unusual properties. They help explain why water remains liquid across such a surprisingly broad temperature range. Similar molecules of comparable size often behave very differently. Without hydrogen bonding, water might evaporate far more easily or freeze under completely different conditions. Instead, it exists comfortably as liquid across the temperature range where Earth's surface operates. That sounds simple until you realize how rare and important that balance may be. A little different, and Earth's oceans might spend most of their existence frozen or vaporized. Life would face an entirely different planet. hydrogen bonds also create surface tension, another strange feature humans rarely think about. Water molecules cling together strongly enough to form droplets, allow insects to walk across ponds, and pull water upward through tiny spaces inside plants. Entire forests depend on this. Trees transport water from roots to leaves, partly through the cohesive behavior of water molecules. The forests regulating Earth's atmosphere today rely on microscopic interactions between molecules humans cannot even see. Even blood circulation and cellular chemistry are tied deeply to water's unusual behavior. It is difficult to overstate how thoroughly biology is built around the assumption that water behaves exactly the way it does. Which raises an uncomfortable question. Why does it behave this way at all? Scientists understand the mechanisms involved, but understanding the mechanism is not always the same as understanding why reality allows such a precise combination of properties to exist simultaneously. Because water is not merely useful for life, it appears almost perfectly suited for it. That realization has led some thinkers into dangerous territory, scientifically and philosophically. Throughout history, people occasionally argued that water's remarkable properties imply intentional design within the universe itself. Most scientists avoid such conclusions because natural selection explains why life adapted to water rather than proving water was made for life. Still, even many researchers admit water's behavior is extraordinary. Astrobiologists searching for alien life often begin with water because Earth's chemistry depends so completely on it. Some alternative possibilities have been proposed: ammonia-based life, methane environments like Titan, or entirely different biochemical systems. But no known liquid matches water's versatility for supporting complex chemistry. Water dissolves enormous numbers of substances. It remains stable across broad conditions. It transports heat efficiently. It supports intricate molecular interactions. And unlike many liquids, it actively participates in biological chemistry itself. In some ways, life does not merely live in water. Life uses water as machinery. And perhaps nowhere does that become stranger than inside the cell. Every living cell on Earth is essentially a controlled water environment. Proteins fold into specific shapes because of how water interacts with them. DNA maintains its structure partly because of surrounding water molecules. Chemical reactions powering metabolism occur continuously in aqueous environments. Remove water, and biology stops functioning almost immediately, which means every organism humans have ever known is fundamentally dependent on one very specific liquid behaving in one very specific way. That dependence becomes even more unsettling when viewed cosmically. The universe contains countless planets, stars, and galaxies. Physical laws allow enormous diversity across cosmic environments. Yet intelligent life on Earth emerged only within an extremely narrow range of conditions where water remained stable and chemically useful for billions of years. A slightly hotter Earth might have become Venus. A slightly colder Earth might have remained globally frozen. A weaker atmosphere, different pressure levels, minor orbital variations. Any of these changes could alter how water behaves across the planet. And once water stability disappears, biological complexity may collapse with it. There is another strange property of water that humans rarely think about because it happens constantly around them. Evaporation cools things. When water molecules escape into the air as vapor, they carry heat away. Sweat works because of this. Ocean evaporation influences weather because of this. Hurricanes gain power partly because warm water transfers energy into the atmosphere through evaporation and condensation cycles. Water continuously moves heat around Earth, like an invisible planetary circulatory system. And those movements helped shape civilization itself. Rainfall patterns determine ecosystems. Ocean currents affect agriculture. Climate stability influences where civilizations rise or collapse. Even human migration history is partly tied to water's strange thermal behavior, all because of a molecule made from only 3 atoms: 2 hydrogen, 1 oxygen. That simplicity may be the most deceptive part of all. Water looks chemically small, yet its collective behavior becomes extraordinarily complex. Under extreme pressures, it forms unusual ice structures unlike ordinary frozen water. In supercooled states, liquid water can remain unfrozen below normal freezing temperatures. At microscopic scales, water molecules organize dynamically in ways researchers still actively study. Even today, scientists continue discovering new details about how water behaves. The deeper they investigate, the less simple it appears. And perhaps that is why water feels strangely different from other substances, emotionally as well as scientifically. Humans instinctively associate it with life, memory, weather, movement, and survival. Entire mythologies formed around rivers, oceans, floods, and rain long before chemistry existed as a science. Ancient civilizations worshipped water because survival depended on understanding its rhythms. But modern science revealed something even stranger than mythology. The ancients were right to sense that water was special. Not magical, not supernatural, but genuinely unusual in ways that may have shaped the entire trajectory of life on Earth. And somewhere inside that realization is a quiet cosmic mystery still unresolved. Because if intelligent life depends so heavily on the precise behavior of water, then perhaps the universe contains countless worlds where biology almost emerged but failed simply because their liquids behaved differently. Maybe oceans existed there too. Maybe rain fell. Maybe rivers carved landscapes beneath alien skies. But without the exact chemical balance Earth inherited, life never crossed the invisible threshold between chemistry and consciousness. Which means every ocean on Earth may represent more than water alone. It may represent one of the rare places in the universe where physics happened to cooperate just long enough for the universe to become aware of itself. Long before humans built cities, wrote laws, or looked at stars through telescopes, water was already shaping the direction of civilization. Not metaphorically, physically. Entire migrations followed rivers. Survival depended on rainfall. Seasons determined by water cycles controlled food, stability, trade, disease, war, and eventually empire itself. Even now, modern civilization still quietly bends around the movement of water in ways most people rarely notice. Because humanity did not simply adapt to Earth. Humanity adapted to water. And the deeper you follow that idea backward through history, the stranger it becomes. The first humans evolved in landscapes where water meant survival every single day. Ancient hunter-gatherer groups moved according to rivers, lakes, wetlands, and seasonal rainfall patterns. In dry environments, finding water often mattered more immediately than finding food. Dehydration kills quickly. Entire routes of migration across Africa and beyond may have depended on narrow chains of water access stretching across otherwise hostile terrain. Some researchers even suspect fluctuating climate cycles helped shape human evolution itself. During periods when rainfall patterns shifted dramatically, forests shrank and grasslands expanded. Human ancestors adapted to changing landscapes, altered food sources, and unstable environments tied directly to water availability. In a strange way, the unpredictability of water may have helped shape the adaptability of humans. And once agriculture emerged, water stopped being only a survival requirement and became something even more powerful. Control over water became control over civilization. The first great civilizations on Earth did not appear randomly across the map. Again and again, they emerged beside rivers. The Nile, the Tigris and Euphrates, the Indus, the Yellow River. This pattern appears so consistently across history that it almost stops looking accidental. Ancient Egypt existed because of the Nile. Every year, floods carried nutrient-rich sediments across the surrounding land, renewing the soil naturally. Outside the river valley stretched deadly desert. But beside the Nile, agriculture flourished. Villages became cities. Cities became kingdoms. Kingdoms became one of the longest-lasting civilizations in human history. The river was not simply nearby. The river was the civilization. Its flood cycles shaped religion, calendars, politics, taxation, engineering, and mythology itself. Egyptian life moved to the rhythm of water rising and falling. The same pattern appeared elsewhere. In Mesopotamia, unpredictable rivers forced societies to develop irrigation systems and coordinated labor on large scales. Managing water required planning, organization, and authority. Some historians believe this pressure helped accelerate the development of bureaucracy, governance, and early states. Civilization grew where humans learned to organize water, and that organization changed human psychology permanently. For most of human history before agriculture, populations remained relatively small and mobile. But once irrigation and stable food systems developed, populations expanded rapidly. Permanent settlements formed. Surplus food allowed specialization. Priests, rulers, merchants, soldiers, engineers, and writers emerged because agriculture created enough stability for societies to become more complex. And beneath all of it flowed water. Even religion absorbed this connection deeply. Flood myths appear across cultures separated by enormous distances and time periods. Ancient Mesopotamian stories described catastrophic floods long before similar themes appeared elsewhere. The biblical story of Noah preserved the same core imagery. Many indigenous traditions around the world contain flood narratives tied to destruction, renewal, punishment, or rebirth. Some scholars believe these stories may preserve cultural memories of real flooding events after the last ice age, when sea levels rose dramatically across parts of the world. Others argue flood myths emerged naturally because rivers and storms were powerful forces shaping early societies everywhere. Either way, water became more than a physical necessity. It became spiritual, mysterious, sacred. Humans feared it because it could destroy entire civilizations overnight. They worshipped it because survival depended on it completely. And the ocean changed humanity in a different way entirely. Rivers created civilizations. Oceans connected them. For thousands of years, the sea represented both terror and opportunity. Ancient sailors crossed waters without understanding storms, currents, or weather systems fully. Entire ships vanished into darkness. Coastlines disappeared beyond the horizon into regions many civilizations considered unknowable or mythical. Yet humans kept sailing because oceans carried trade, wealth, ideas, and power. The Mediterranean Sea became one of the great engines of ancient civilization. Greek colonies spread across its shores. Phoenician traders connected distant regions. Roman expansion depended heavily on maritime control. Whoever dominated important waterways often dominated commerce itself. And as navigation improved, the oceans transformed from barriers into highways. The age of exploration reshaped global history largely through water. European powers crossed oceans seeking trade routes, wealth, territory, and influence. Entire continents became connected through maritime networks. Foods, diseases, technologies, languages, and empires moved across the planet through shipping routes carved into the sea. Modern globalization began on water. And there is something unsettling about realizing how fragile all of it remained. Entire civilizations have collapsed, partly because water systems changed. Drought weakened agricultural societies repeatedly throughout history. Some researchers suspect prolonged climate instability contributed to the collapse of the Maya civilization in parts of Central America. Severe droughts affected dynasties in ancient China. Dust Bowl conditions devastated parts of the United States during the 20th century. Water scarcity destabilizes societies because it attacks civilization at its foundation. Food production declines. Migration increases. Conflict intensifies. Political systems weaken. And despite all modern technology, humanity still depends on freshwater systems that are surprisingly fragile. Most of Earth's water is saltwater. Most freshwater is locked inside glaciers or underground reservoirs. Only a tiny fraction remains easily accessible for human civilization. That imbalance becomes more disturbing the larger human populations grow. Modern cities consume extraordinary amounts of water every day. Agriculture, industry, energy production, transportation, and sanitation all depend on stable water access. Entire economies quietly assume that rivers will continue flowing and rainfall patterns will remain predictable enough to support civilization. But climate systems are changing. Glaciers feeding major rivers are shrinking in some regions. Aquifers are being depleted faster than they refill. Droughts intensify across parts of the world, while floods grow more destructive elsewhere. Sea levels rise slowly but continuously. And suddenly, humanity finds itself confronting an ancient truth again. Civilization is still dependent on water in ways technology never fully erased. The difference now is scale. Ancient kingdoms collapsed regionally. Modern water instability could affect billions. There is another psychological layer to this relationship humans have with water that runs deeper than survival alone. People are instinctively drawn toward it. Most major cities exist near coastlines, rivers, or lakes. Humans build homes beside water when possible. The sound of rain relaxes many people. Ocean waves affect mood. Researchers studying psychology sometimes discuss the blue mind effect, the calming mental response humans often experience near water environments. No one knows exactly why this connection feels so deep emotionally, but it may trace back to evolutionary history itself. For countless generations, water represented safety, food, movement, and survival. Human brains may still carry ancient responses shaped by that dependency. Even language reflects it. People describe emotions as waves. Memories flood back. Thoughts drift. Time flows. Human consciousness borrowed the behavior of water to describe itself. And perhaps that makes sense, because in many ways, civilization behaves like water too. It spreads, connects, erodes barriers, changes shape constantly while still remaining recognizably itself. The deeper you look into history, the harder it becomes to separate human development from water entirely. Empires rose because of rivers. Trade expanded because of seas. Wars began over access to water routes and fertile land. Religious rituals centered around purification through water. Industrial revolutions accelerated beside waterways powering factories and transportation systems. Even modern internet infrastructure depends partly on underwater cables crossing oceans beneath the seafloor. The digital age still follows water. And perhaps the strangest realization of all is that humans often speak about conquering nature while remaining completely dependent on the same ancient planetary systems that shaped the first civilizations thousands of years ago. Water still determines where millions can live, still shapes economies, still influences migration, still decides whether crops survive, still destroys cities through storms, floods, and rising seas. Humanity became technologically advanced, but it never escaped the rules of the planet. And somewhere inside that truth is a quiet reminder of how recent civilization actually is. The oceans existed for billions of years before humans appeared. Rivers carved valleys long before language existed. Rain fell on earth long before consciousness evolved to hear it. Human history may feel enormous from our perspective, but beside the age of water itself, civilization is almost unimaginably young. A brief moment of awareness beside ancient seas that were already shaping worlds long before humans learned to name them. Right now, the oceans feel permanent. Waves continue rolling onto shorelines exactly as they did before the first cities existed. Rain still falls. Rivers still cut slowly through mountains. From a human perspective, water seems eternal, part of the basic structure of reality itself. But Earth's oceans are living on borrowed time, not because humanity will necessarily destroy all of them tomorrow, not because drought will suddenly empty the seas, but because the universe itself does not keep planets stable forever. And one day, far in the future, Earth may lose its water completely. That idea sounds impossible at first. After all, the oceans are enormous. Water covers most of the planet. Ice exists at the poles. Clouds circulate endlessly through the atmosphere. The global water cycle feels unstoppable. Yet, from the perspective of planetary science, Earth's current state is temporary. It always was. The story begins with the sun. Every second, deep inside the sun's core, hydrogen atoms fuse together under immense pressure, releasing energy outward into space. That energy is what powers Earth's climate, weather, oceans, ecosystems, and life itself. But the sun is not perfectly stable across billions of years. As stars age, they slowly change, and our sun is gradually becoming brighter. Not dramatically within a human lifetime, but steadily across geological time. Scientists estimate the young sun billions of years ago was significantly dimmer than it is today. Earth's climate survived partly because greenhouse gases helped trap additional warmth. But over immense stretches of time, solar output continues increasing, which means Earth's future grows hotter, even if humans vanished tomorrow. At first, the changes are subtle. Oceans evaporate slightly faster, weather patterns shift, climate zones move. But eventually, somewhere in Earth's distant future, the balance keeping liquid water stable may begin breaking permanently. And once that process fully starts, the planet could slowly move toward the same kind of catastrophic greenhouse conditions that transformed Venus long ago. The terrifying part is how ordinary the beginning might look. More evaporation means more water vapor entering the atmosphere. But water vapor is itself a powerful greenhouse gas. It traps heat efficiently. More trapped heat causes more evaporation. More evaporation creates more water vapor. The cycle intensifies gradually. At first, oceans still exist. Storms continue. Clouds still form. But the atmosphere grows thicker with moisture and heat. Eventually, temperatures may rise enough that large portions of Earth's oceans begin evaporating continuously, faster than they can stabilize. The sky itself could become increasingly heavy with steam. Earth would start resembling the ancient world from billions of years ago. The same violent, steam-covered planet that existed before stable oceans first formed. Except this time, the process would move in reverse. Not oceans appearing, oceans disappearing. And somewhere high above the atmosphere, another silent process would begin. Ultraviolet radiation from the sun can split water molecules apart. Hydrogen escapes into space relatively easily because it is so light. Oxygen reacts with surface materials or atmosphere below. Over immense spans of time, Earth could slowly lose water molecule by molecule into space itself. The oceans would not merely dry up. Parts of them would literally leave the planet forever. That possibility changes the emotional scale of Earth entirely. Humans often imagine oceans as ancient, but from a cosmic perspective, they may actually represent a temporary phase in planetary evolution, a rare middle state between molten worlds and dead, dry planets. Some models suggest this transition may begin seriously within about 1 to 2 billion years, though exact timelines remain debated. Long before the Sun becomes a red giant, Earth could already become increasingly hostile to complex life. Plants may struggle first. As temperatures rise and carbon cycles destabilize, ecosystems could gradually collapse. Oceans warm. Oxygen levels in seawater shift. Climate extremes intensify. Complex organisms disappear progressively as habitable regions shrink. The final living things on Earth may not resemble humans at all. Microbial life could survive long after large ecosystems collapse. Deep underground bacteria or extremophiles near hydrothermal vents might persist in isolated environments while the surface becomes increasingly hostile. Life may retreat downward as the planet heats upward, and eventually, perhaps only traces remain. Dry ocean basins. Mineral deposits where seas once existed. A thickened atmosphere above a planet growing steadily more silent. Yet strangely, even this future is not guaranteed in every detail. Planetary systems are complicated. Geological feedback mechanisms, atmospheric chemistry, cloud behavior, tectonic activity, and biological influences interact in ways scientists are still studying. Some uncertainties remain about how quickly various transitions might unfold, or how stable Earth's climate systems may stay across extremely long timescales. But the overall direction appears difficult to escape. The Sun will continue changing, and Earth cannot remain exactly as it is forever. Then comes an even more surreal phase. Billions of years from now, the Sun itself will exhaust much of the hydrogen fueling its core. As it enters later stages of stellar evolution, it will expand dramatically into a red giant. Its outer layers will swell outward across the solar system. Mercury will likely vanish first. Venus almost certainly disappears. Earth's fate remains slightly uncertain in precise detail, because mass loss from the Sun may shift planetary orbits outward somewhat. But even if Earth physically survives being engulfed, the oceans would already be long gone by then. The surface would be unrecognizable. No blue planet, no clouds, no rivers, possibly not even continents resembling modern Earth. Just scorched rock beneath an enormous dying star filling much of the sky. And there is something haunting about realizing the oceans humans know today exist during only a narrow window between two extremes. At the beginning of Earth's history, the planet was too violent for stable seas. At the end, it may become too hot again. All of human civilization exists between those two eras. A temporary age of water. That realization also changes how scientists search for life elsewhere in the universe. When astronomers look for exoplanets, they are not simply searching for planets with water. They are searching for planets existing inside the right window of time. A world may once have had oceans and lost them. Another may still be frozen before liquid seas emerge. Some planets may only remain habitable for relatively brief periods before stellar evolution destroys stability. Habitability may not just depend on place, it may depend on timing. And perhaps Earth's greatest cosmic luck is that intelligent life emerged during the exact period when oceans, climate, atmosphere, and sunlight all aligned long enough for consciousness to appear. Because if humans evolved much earlier, Earth might still have been hostile. Much later, the oceans may already be fading. There is another unsettling thought hidden beneath all this. The universe itself may eventually become increasingly dark and cold over unimaginable timescales. Stars burn out, galaxies drift farther apart, energy becomes harder to use. The long future of the cosmos may contain fewer environments capable of sustaining liquid water at all. Which means oceans could be temporary, not just on Earth, but cosmically. Brief islands of chemistry and memory appearing between vast eras of darkness. And yet, despite all this, water may still outlive civilizations many times over. The oceans have already survived asteroid impacts, supervolcanoes, ice ages, mass extinctions, shifting continents, and hundreds of millions of years before humans existed. Civilizations rise and disappear almost instantly compared to planetary time. Even modern humanity represents only a tiny flicker beside the age of Earth's seas. The Atlantic Ocean existed before language, the Pacific before mammals. Rain was already falling on Earth long before the first human ancestor ever walked upright beneath the sky. And one day, long after humanity is gone, waves may still continue breaking against coastlines under a brightening sun for millions of years more, until eventually, slowly, the sky itself begins taking the oceans back. Perhaps that is the strangest emotional truth hidden inside the story of water. The oceans feel eternal because human lives are short. But from the perspective of the universe, even entire seas are temporary things, and all of human history may simply be a brief moment when a cooling planet circled a stable star with just enough water left for the universe to become conscious of itself before the oceans disappear again into silence. Thanks for spending this time exploring the hidden story of water with me tonight. If you enjoyed this journey through Earth's oceans, ancient storms, and cosmic mysteries, don't forget to subscribe to Sleepy Origins for more relaxing documentaries like this. Wherever you are in the world tonight, I hope you have a peaceful evening, a calm mind, and a good night's sleep.